Now, the final part of this particular topic on probability brings us into an area of overlap between probability that we've been studying for the last number of days and statistics, which we have yet to study. Okay, and basically what we're going to study here is how a natural distribution of data can be used in order to predict probability. Now, it seems quite a difficult way to merge the two, but how a natural distribution of data can be used in order to predict a probability. And just before we do that, this particular picture I have here, this is called a Galton board, okay? And a Galton board is nothing more than a board with an increasing number of pegs in straight lines, so forms a triangle, and spheres being dropped simply under the influence of gravity. All right. Now, the spheres themselves, they have a 50-50 chance of bouncing to the left or bouncing to the right. And what we notice just from this snapshot here is that there tends to be a gathering of these spheres in the center of this particular bar chart. So they seem to fall through the center. Yes, some of them deviate out towards the edges. So you can see that it begins, there are bars out on the 13 and on the 3 level. There's a bar there, okay? But the majority of these spheres, they tend to centralize. And that means then that when we have a random flow of these spheres, the natural way for them to settle is symmetrically around the middle. Okay, so I'm just going to take a look at this. I think we can actually make this live. I hope we can. Yes, we can. Okay, let's just have a look at this. And I want you to take a look at how these things bounce. Now, first of all, notice up here, if you can see it, that there is a 50-50 chance of bouncing left or right. Now, we could skew that, and I'll talk about skewed in a moment. We could have a 25-75 where they bounce to right more so than they would bounce to the left, and therefore you'd have a gathering over on the right-hand side. But here, there's a 50-50 chance of them bouncing to the left or to the right. But what we notice is that even though they have that opportunity to go left and right, they seem to be centralizing. They seem to be falling into the center area, which is giving our bar chart below a very interesting shape. Now, I'm just going to speed this up slightly because otherwise we'll be here all day. I'm going to speed it up if I can. Yeah. And I'm just going to let you watch the bar chart as it's produced. Okay. You'll notice that there's a tendency for these spheres to centralize. Okay. What we actually end up getting, if we were to allow enough of these in, what we would actually get is a curve that is perfectly symmetrical around the central value. In other words, as long as the spheres are allowed to fall randomly under the natural force of gravity, they will tend to gather symmetrically in a symmetrical curve around a central value. And that particular bar chart that we have there is a very crude, what we would call natural distribution, or a natural curve, okay? Or a normal curve is probably the more correct mathematical term to give it, or a normal distribution. So you can play around with that yourselves. It's on the slides. You can click the link and go into it and see exactly how it works. So I'm going to come back to the slides. Now, first of all, as we told you already, this is a Galton board, okay? Nothing more than a triangular array of pegs, so it means a collection of pegs. The spheres are dropped onto the top peg and bounce their way down to the bottom where they're collected in bins. Each time one of these little spheres hits the other pegs, it bounces left right with the same probability. So the probability going left and right is 0.5 and 0.5, okay? When there's an equal chance of bouncing left or right, we notice that they collect centrally. Now, centrally means that they collect around a center value. We know from our junior cert that the center value, one of the center values of an array of numbers or a collection of data is the mean. And that's what's happening here. They are collecting around the mean value and they're deviating into further fields which are apart from the mean on a far less scale than they're gathering around the mean. So the mean is where the majority of spheres will go. Yes, we'll have deviations. Some of them will bounce out to the peripheries and fall down in the 0s, 1s and the 13s and 14s, but very, very few compared to what centralizes. All right. So therefore, if you have a symmetrical curve where the data is symmetrically gathered around a central value and it's produced randomly and naturally, that is what we call a normal curve. Okay, and normal curves are found in nature. Anything that is naturally distributed, for example, IQ or height or body mass, anything like that at all that's naturally distributed is a normal distribution. and it always gives rise to this curve. Like it or like it not, your leaving cert results are going to be forced into a normal curve, because if there's a normal distribution of IQ, well, then there should be a normal distribution of exam results. So your exam results are a typical example where the results, they fit into this curve, where the majority of students fall into the middle, and then you've got the few little, what we would call deviations. Those who score very, very low and those who score very, very high, but they're quite few and far between. So those little bars representing those people would be quite low. When the probabilities are not even, then we end up getting something that is skewed. And let me just show you what a skewed diagram would look like. Let's just skew this thing. Let's take a 75, if I can bring it up there, right, a 2080. Okay, let's reset that. Restart. Now, we're going to take a speed. Let's just take, there's an 80% chance now that they're going to pop to the right hand side. So you can see straight away that the diagram is no longer normally distributed. The diagram is now skewed towards the right hand side because I have mathematically skewed it in my probability. I've given a 20% probability jumping left and an 80% probability of jumping right. So now my data is skewed, okay? And that type of skewed diagram does not represent something that's natural or normal. There's a bias involved, and the bias is obviously a 20-80% split in favor of the spheres bouncing towards the right hand side. Okay, so data therefore can be distributed in many ways. It can be distributed, there's three different ways. First of all, we notice here that we have data peaking after, down here, okay, down up to the higher positive regions. Now a situation like that, we find this out later on in statistics, where the tail leads. That's what we call the diagram. So this would be negatively skewed, okay? And then here, the tail is leading into the positive area that way, so that's positively skewed. And here, because there's no real pattern, that is what we would say is random, okay? So just keep that in mind. We'll meet that again later on. There tends to be many cases where the data can be gathered around the central value. We talked about this already. When you notice that your curve is symmetrical and the data has gathered symmetrically around the central value, which we call the mean, that's a normal curve, and that's what we're going to look at. There it is, okay? That's what we call a normal curve. It's called a bell curve because if you were to draw a bell, I'm not used to drawing anything, you get a bell like that. And the bell then obviously would ring, etc., etc. So that's where we get the idea of a bell curve from, all right? It looks like the shape of a bell. So it's called a bell curve, or it's called a natural or a normal distribution. Many things closely follow natural distributions, we said already. Heights of people. So there's an example of where you have a number of people of all various different heights, okay? The red line would represent the mean, and then you've got people who are closer to the mean, people who are further away from the mean, and those people who are not the mean height will be deviating from the height, so they will be further out from that central value on our normal curve. Size of things produced by machines, errors in measurement, blood pressure, okay, that's again, it's a normal distribution because it's a natural phenomenon, and marks on a test. If IQ is natural, then the marks on a test are going to be normally distributed. So if we take a human IQs, if we were to gather all the IQs of the humans around the world and put them all onto a diagram, this is what we would get, where we would expect that the majority of people would have what we would call an average or a mean IQ. And then people with a lower IQ would be to the left-hand side. People with a higher IQ would be to the right-hand side. But the number of people with a very low IQ is extremely low. Likewise, the number of people with a very high IQ is very, very low as well. So there's a symmetry here, okay? The majority of the world's population, we would hope, are gathered symmetrically around the mean IQ, which means the majority of the world's population is in this space here. And we'll talk more about these little lines that I've drawn there in a few moments. The normal distribution has the mean being the same as the mode, being the same as the median. Now, again, I'm not going to worry about this until statistics begins, but just to bring those three M's back into your head, the mean, the mode, and the median, they are three ways of measuring center. And when your normal distribution or your normal curve is symmetrical, well, then they line up. The mean, the mode, and the median are exactly the same value, okay? But only when it's symmetrical. The normal distribution is a symmetry about the center. 50% of the values that are less than the mean will obviously be on the left-hand side. 50% of the values greater than the mean will be on the right-hand side. So you end up with something like this. There's your normal curve with the mean, the mode, and the median slap bang in the center. And then because of the symmetry, we've got 50% of values below the mean and 50% of values above the mean. So when we roll a pair of dice and then we add the two numbers that come up, some outcomes are more likely to occur as this table shows. Now I want you to look at this, okay? Just take a look at this. If we have two dice, say we've got a green one and a red one, and say that we throw them, and every time we throw them, we simply count up what they add to. All right, here are all the possible outcomes. So you could have a 1 and 1, which will give you 2. Then you could have a 1 and 2, which will give you 3. But you also might get a 2 and 1. So if the red is 2 and the green is 1, that's 3. If the red is 1 and the green is 2, that's still a 3. Okay, but there's a pattern here. Watch. That's 2. Both of them are 3. The 3 of them are 4. 4 of them are 5. Get the idea? So there's a pattern here. Now I'm going to show you a table. I'm going to fill this in, all right? How many of these boxes have dices that sum to 2? Well, the answer is just 1. Just put a 1 there. How many of these boxes have dices that add to 3? Well, these two. Notice my diagonals. I'm going to put more of these diagonals in here. And then this one. And this one. This will just help me to speed up the process. Okay. How many of these boxes have dices that add to 4? Well, 1, 2, 3. How many add to 5? 1, 2, 3, 4. How many add to 6? Well, we go, and you get the idea. So we get to add to 6. 1, 2, 3, 4, 5. See what happens? So if I was to go all the way as far as 12, what would I get? I'd get 2, 3, 4, 5, 6. I'd get 1, 2, 3, 4, 5. And then, watch what happens. When I get to 7, 6 and 1. 1, 2, 3, 4, 5, 6. Now, what happens when I get to a sum of 8? How many dice here make up 8? 1, 2, 3, 4, 5. It starts coming down again. So I get 1, 2, 3, 4, 5, 6, because the highest sum is going to be 7. Then on the other side, it comes down again 5, 4, 3, 2, 1. So in other words, when I finish this table, you can do that yourselves. When I take that, what I notice is a sum of 2 only gives one result, but a sum of 12 only gives one result. Yeah? A sum of 3 gives 2 results, so therefore a sum of 11 would give 2 results. So there's symmetry. Beautiful symmetry going on this way. And when I plot all those results, I end up getting something like this. So there are, as we said already, there's the number of ways we can get a sum of 7. There's the number of ways we can get a sum of 2. There's the number of ways we can get a sum of 12. So there's a lovely symmetry. And again, if I was to join these, what would I get? I'd get a normal curve. Why? Because there's no bias in the dies. They fall naturally. If they fall naturally, then we're guaranteed that these will give a normal curve. And there's a normal distribution of sums between two die anyway. So that's why we see it. Now notice, in this case, it's jagged, and there's a reason for that. The reason for that is because dice only have certain values, 1 to 6. There's also such thing as throwing a die and getting 4.5, or getting 3 3/4. So there are only whole numbers, natural numbers between 1 and 6 available to sum. So therefore you can only get whole number answers. All right. But if we were to take some type of natural phenomenon, for example, like height, okay? Say we're to take height. When you stand up and take your first steps, you're a certain height. By the time you get to 21, you've reached your peak adult height. Now, is there any height between those two that you couldn't have been? Did you skip any heights? And the answer is, of course, no. So therefore, from the time that you stood up to the time you reach your maximum height, every single height between those two has been covered by you because you've grown, okay? That's called continuous data because you go through every possible value between your lowest height and your adult height, okay? So when we use discrete values, when they're definites like a dice, we get this jagged type of affair like this thing here. But when we use continuous data like body mass or like height or like IQ, we end up getting a graph that looks much, much more smooth and much more in line with our natural curve than we had before. Okay, so here's an example of where I have a graph and I'm after taking a group of people together and I'm after taking nothing more than their body weight, okay, or their body mass. Now, when I plot that, here's what I notice. The mean is 200. So the mean is 200. So therefore, most people will have a body mass of 200 pounds. There will be people who have a body mass of 100, but they'll be very, very small in number. And there will be people who will have a body mass of 300, but they'll be very small in number. But because body mass is a natural phenomenon, we get a natural curve. And again, we see the beautiful symmetry. the numbers on the left-hand side are the same as the numbers on the right-hand side, okay? And that means the symmetry will help us then, this bell-shaped curve will help us in calculating probabilities at a later stage. In any body of naturally occurring or normally distributed data, now what I mean by that is things that are random and non-biased, there is a mean, which is the one measure of the centre that we're going to focus on. So the mean, the mode, and the median, they're three measures of centre. I'm only interested in the mean, okay? Because the mean is a way of measuring the centre of all of this particular data that we've gathered. If you do not have the mean value, then you're deviated from that. So just go back to this diagram here. If you don't have a body mass of 200 pounds, then you're deviated from the mean. If you do have a body mass of 200 pounds, then that means that you are slap bang on the mean. The further away from the mean you actually are, the more deviated from the mean you are, okay? So therefore, people of 300 pounds body weight and 100 pounds body weight will be equally deviated. They'll be the most deviated from the mean because the 100 pounds will be the lightest and the 300 pounds will be the heaviest, okay? So the further away you are from the actual mean, the more deviated you become. And that word is important, so we'll talk about that word now in a few moments. The standard deviation, therefore, is a measure of how the data is spread around the mean. So in other words, we have to have some way to distribute those who have not got the mean body weight in this case here. How do we distribute them? And the answer is we distribute them by using what's called a standard deviation. Now, the standard deviation is a number, and it's a number that is a certain number of units above the mean and a certain number of units below the mean, but it's symmetrical, okay? And I'm not going to worry about calculating it now because that's in the next chapter, so we don't worry about calculating it. They will give it to us in the questions that are about to occur. But the standard deviation is a measure of how your data is spread around the mean. And if it's a normal distribution, when you use your standard deviation, you get a beautiful bell curve. The symbol for the standard deviation is this one here, sigma. Okay, so keep that in mind. It's sigma, and we'll use sigma in a moment. So for example, take this here, and let's just see if we can work out what this is trying to tell me. This is the time taken to deliver a pizza after you've ordered it. Okay, now why do I pick pizza? Because I like pizza, simple as that. So this is the time taken of a pizza to be delivered after you've ordered. And we asked a load of people, how long did it take your pizza to be delivered? How long did it take your pizza to be delivered? And so on. The mean, which is the line straight down the middle, is 30. So for the majority of people, they said about 30 minutes, okay? Of course, there would be super fit cyclists who are delivering your pizza in record time. They're down here, but they're very few and far between. And then you've got the people up here who decide not to cycle to deliver your pizza and decide to go for a walk with the pizza under their arm. But they're very few and far between. So what this graph is trying to tell me is that in the majority of cases, the delivery time was a half an hour. Now, I want you to take a look at the dotted red lines on either side. The dotted red lines are at definite intervals, and those definite intervals are one standard deviation each. Okay, so we would say here that this has a mean of 30 minutes with a standard deviation of 5 minutes. And notice that it's 5 minutes either side, meaning that the majority of people got their pizzas bang on 30 minutes. Then the next biggest cohort got their pizzas between 25 and 35 minutes. Now, there's an empirical formula, an empirical rule that we use in statistics, which tells us the following, that between these two, if you take one standard deviation either side, that covers 68% of your population. Okay? If you take two standard deviations either side, well, that will cover 97% of your population. And if you go 95 I should say, 95. And if you go 3 standard deviations either side, you'll get 99.7% of your population. So if I was to try and make sense of this, here's what I'd say. Most people got their pizzas bang on 30 minutes. Okay, that's the average, the mean time. 68% of the people I asked got their pizzas between 25 and 35 minutes. That's one standard deviation either side of the mean. 95% of the people I asked got their pizzas between 20 minutes and 40 minutes, because that's 2 standard deviations either side of the mean. And lastly then, 99.7, which is nearly the entire cohort of people I asked, got their pizzas within 15 minutes with the super guy and 45 minutes with the guy outside sitting on his arm and walk. Okay, but you notice The standard deviation is a value. And the number of standard deviations we take either side, the maximum number is 3. So we always take 3 above and 3 below. And the number of the standard deviation is something that we calculate based on the data we're given, something that we look at later on. Okay, so for example, take this one here. Now, what does this try to tell me? Well, this tries to tell me now that the mean IQ for the world's population is roughly 100. Okay? Now, what does the 2 bars mean? Here, my standard deviation is 15, and notice that it's 15 either side. Okay? And in here, you have 67% of the world's population. So 67% of the world's population will have an IQ between 85 and 115, which is 1 standard deviation either side of the mean. Okay? If we move to the next two, 95% of the world's population will have an IQ between 70 and 130. And if we move to the third bar, that takes in 99.7% of the world's population will have an IQ between 55 and 145. Well, we would hope so. So in other words, nearly everybody is represented in that graph when we move out to 3 standard deviations either side. Okay. What's the mean IQ? 100. What's the standard deviation? Well, what's that symmetrical gap either side here? 15. So if we go 1 standard deviation either side, that's 68% of the world's population. If we go 2 standard deviations, that's 95% of the world's population. And if we go 3 standard deviations either side, we've captured 99.7%, which is good enough to represent the whole lot. Okay, even though it's not the whole thing, it's good enough to represent it. So here's what we've discovered, as I told you already. 68% of the world's population will be within the mean and 1 standard deviation either side. 95% of the world's population will be 2 standard deviations either side of the mean, and 99.7% of the world's population, or whatever you're counting, whatever data you're taking, will be within 3 standard deviations either side of that particular mean. That's the empirical rule. More about that later. Not really interested in that now. So, what about the normal distribution table? Now, in your tables, your formulas and tables book, on page 36 and 37, there is a very important set of values that as yet we haven't looked at, and that's called the Z-score table. Okay, now here's the problem. When I'm taking naturally occurring data like body mass or like IQ or like height, they're all measured in different ways. So body mass is measured in kilograms, height is measured in centimeters, and so on. But therefore, how do I represent different units on the same curve? And the answer is that we've got to standardize these particular values. And the way in which we standardize them is by using a Z-score. So when you take a bit of data from somebody, you then bring that back in line with the mean and the standard deviation, and you convert it into a Z-score. And only then does that piece of data have use on what we would call your normal distribution table. Okay, so a statistic with Z equals 2.4 would be 2.4 deviations above the mean, and a statistic with Z equals minus 1.67 is 1.67 deviations below mean. So let's just say, for example, that the average IQ is 100, and I take somebody with an IQ of 130, okay? And let's say that the average IQ is 100, his IQ is 130, the standard deviation is about 10. When I do a calculation on that, I'll get a value of, let's say, 1.27. What does that Z-score tell me? That Z-score tells me that this guy's IQ is 1.27 standard deviations above the mean. So the Z-score is giving you a position on the natural curve as to where this IQ or body mass or height is going to be. So we can actually see it, okay? The tables, as we said already, page 36, page 37, have a table that will allow you then to turn these Z-scores into probability, and we'll connect the two in a few moments. Okay, one very important thing to remember, the last sentence here, and this is extremely important. When we are turning a Z-score into a probability, we have to take the area that is under the curve, the natural curve, but to the left of the mark that we place on the normal curve. So again, I go back and say, if a guy has an IQ of 130 and the average IQ is 100 and the standard deviation is 10, okay, that is going to bring me to 3 standard deviations outside the mean. So we will mark it on the natural curve, a normal curve, and then from that we can use the tables to calculate the area that is to the left of that line underneath the normal curve. So There's a representation of your tables. There it is there. And up here, which we'll talk about again in a few moments, is your formula. And your formula is Z. If you want to take a statistic and turn it into a Z-score, you take the statistic that you have measured, you take away the mean for that particular body of data, and you divide it by the standard deviation. The lovely thing here is all of this is going to be given to you. Okay, you don't have to worry about anything. So, what is PZ of, what's the probability that Z is less than or equal to 1.36? Now, here's the steps that we take, okay? Because this is a Z-score, I don't have to do any changing. It's already Z, so I can use the table straight away. It's only if they gave you something like kilograms or centimeters or IQ units, then we'd have to change them. But here, when they give you a Z-score, you go straight to the tables. First of all, where is 1.36 on this particular curve? Well, 1.36 is roughly, it's about there, okay? Now, you don't have to be precise. That's about 1.36. Now, what's the probability that Z is less than or equal to 1.36? So, if that's Z, the probability that it's less than or equal is all this area here. See that? Because that's less. So, we're moving this way. And the lovely thing about this is that the tables give you the answer straight away. So, I look up 1.36 over here. So there's 1.3, and then I move in until I get that 0, 1, 2, 3, 4, 5, 6, and there it is. Yeah. So 1.36 has a probability below it of 0.9131, better known as 91.31%. So there's a 91.31% that Z is going to be less than or equal to 1.36. Okay? Good. Let's take another one. What is the probability that Z is less than 2.89? Now, first of all, again, step number one, where is 2.89? 2.89 is up here somewhere. So that's 2.89, and that's your Z score. The probability that Z, again, is less than or equal to is all this area here. And again, because it's to the left, we read the tables directly. 2.89, find it on your tables. 2.8, so we start on this line, and then we go under 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. 9981. So that's equal to 0.9981. Or if you want to say it, 99.81%. So the probability that Z lies below 2.89 on this normal curve is 99.81%, which makes perfect sense. Look at the diagram. Look, there's only a tiny amount of that curve left above Z. There's a massive amount of it below it, so we expect the answer to be quite high. Okay, notice on your tables, and notice in the tables that you have, the book of tables that we use in school, that all the Z scores are positive. But there's your mean, there's one standard deviation above, there's one standard deviation below. The standard deviations below are negative readings. So, for example, if somebody said to you, well, what's the probability that Z is below minus 1.65? You go to your tables and there is no minus 1.65. So therefore, we have to use the whole thing I spoke about at the beginning here. We have to fall back on symmetry. Okay, and symmetry is what's going to get you through this. So let me just take off those annotations. Okay, so what is P, the probability that Z is less than or equal to minus 1.65? Step one, mark it on your normal curve. Okay, where is minus 1.65? Well, minus 1.65 means 1.65 deviations below the mean. So it's down here somewhere. It's about there. That's minus 1.65. And that's the Z score I'm looking at. Now, what's the probability that Z is less than or equal to that? So in other words, what's the probability down there? What's that area? Go to your tables. There is no minus 1.65. But if we think about symmetry, isn't it true to say that the area I have shaded there is exactly the same area as what would be above 1.65 here? So if I was to deal with 1.65 here as my Z score, that area would be this one here. Correct? And therefore, what I could do, let me just take this here, let me take these off, because we've moved it out now to this part. So what I could do instead, if I want to work out what this area is, wouldn't it be 1, the whole thing, minus the area behind it? Because don't forget, z-scores in your tables only give the area to the left. They don't give the area to the right. So therefore, if I look up 1.65 in my tables here, 1.6 and 0, 1, 2, 3, 4, and 5, I get this, 95.05%. But that happens to represent here, 95.05%. That's all of this area. So the shaded region must be 1, the whole thing, minus what I don't want, the 9505. And therefore, let me get my trusty calculator very quickly, wherever she is. She is here. If I just do that quickly, 1 minus 0.9505, that comes out as 0.0495, which is nothing more than 4.95%. Okay, now practice will get you through this. So if they give you a negative z number, we can't use it. It's not in the tables. So go to the positive form and use symmetry. Use the area above. But because the area is above and the tables only give you the area below, use what we used to use, a probability 1 minus the area to the left that we don't want in order to give you the area to the right hand side. Okay, let's try another one. What is the probability that z is greater than or equal to minus 0.22? Now, step number 1. It's a z-score, yes. Find it on your normal curve. Where is minus 0.22? Well, minus 0.22 will be kind of here. All right? It'll just be a little bit below 0. So that's your z-score there of minus 0.22. Question says, what's the probability that z is greater than or equal to minus 0.22? Now, let's think about that. First of all, there is no negative z-scores in my tables. So what I'm going to do is I'm going to change that, symmetrically speaking, to here, to 0.22. And the area that I'm looking for here, yeah, is exactly the same. Sorry, let me just do that again. Okay, so minus 0.22, so we're here. So that's your minus 0.22, okay? There is no z-score in your table for minus 0.22. And what do we want? The probability z is greater, so we want this area here. See, we want all that region there. Now, we're going to have to try and reverse this. So that area there, just think about that, that area there would be exactly the same, let's use symmetry here, as the area behind 0.22 positive. It'll be the same as this. And the lovely thing about that is that is in the tables, because 0.22 is positive and the tables give me the area to the left. So all I've got to do now is go to the tables, find 0.22, and when I find 0.22, there's 0.2, so 0.22 is this one here, which means there's 0.5871, which is the same as 58.71%. Now you can give your answer back as a decimal, you can give your answer back as a percentage, whatever you want to do yourself. It's equally okay. So it's either 0.5871 or it's 58.71%. You decide what that is. So keep in mind, z-scores on the tables are only for positive z-scores. So therefore we involve symmetry for the negative z-scores. And if it's a case that you're looking for an area which is to the right of a z-score, then we use 1 minus whatever the area will be to the left of that z-score. So we'll do a couple more of these in a few moments. So symmetry, as I said, symmetry is extremely important. So let's take a look. Assuming that z is normally distributed with a mean of 0 and a standard deviation of 1, find the following. Now, let's try this one first. What's the probability that z is less than 1.22? Z-score is positive, good, it's on the tables. Number 2, find it here. 1.22 is about there. Okay, so that's 1.22 z-score. Now, we want the probability that z is less than 1.22, and that's fine as well, because that's all the area that's here, below it. And my tables give me that straight away. So I go to the tables, and I'm going to use the tables in front of me here now, not the ones on the slide. You can jump back to slides if you want to. 1.22 and 1.22 will give me 0.8888. So 0.8888, and that's the answer to that one. Okay. Okay, next one. What's the probability that z is greater than or equal to 2.37? Now, is z-score positive? Yes. Good. Mark it. 2.37 is about here. Okay, so that's 2.37, and that's the z-score I'm looking for. However, they want the probability that z is above that. So in other words, they want this thing here. Now we've got a problem. The tables only give me areas to the left. So the tables will work this way, but I want the area to the right. So therefore, the easiest way to get the area to the right is to get the area of the whole thing, which is 1, and take away from that the probability that z is less than 2.37. So in other words, take all of that as 1 and remove what is to the left of 2.37. So now you can go to your tables, and 2.37 on your tables, 2.37 is 0.9911. So if I want to get this area here, you can see straight away that that doesn't match up. That's not 99%. No, it's 1 minus 99%. So 1 minus 0.9911 comes out as 0.0089. So in other words, 0.89%. That's it. Okay. Next one. I'll leave you for you to do, well, minus one. I'll do one more minus one. Actually, I'll do the last two of these. The probability z is greater than minus 0.56. First of all, where is it? Well, minus 0.56 is here, roughly. That's about minus 0.56. Okay, so there's your mean at 0. Problem. Z-scores in the tables are not negative. So what they're asking me here is, look carefully, the probability that z is greater than or equal to minus 0.5. So they're asking me to get this here, all this side. Now, this is where symmetry comes in. Number one, tables don't do negative z-scores. Number two, they don't give the area to the right-hand side. But minus 0.56 with an area to the right, surely at this stage you should begin to understand, is exactly the same as 0.56 with the area to the left. See, you're just using symmetry, not 0.56. And that is in your tables, and your tables do give the area to the left-hand side, so I simply go to the tables. And 0.56 from my tables is 0.7123, which represents 71.23%. Okay? Okay, I'm going to leave that last one for you to do yourselves. You can have a look at that one, part D. If you've got a problem with it, you can come back to me. I want to take one more, which involves two boundaries. Okay, so take a look at this. Take the following. Assuming that z is normally distributed with a mean of 0 and standard deviation of 1, fine. Now, just in case you're wondering, what the hell is a mean of 0 and standard deviation of 1? That's a normal distribution. The mean is slap bang in the middle, and the standard deviation, the data, because it's 1, the data is symmetrically gathered. So in other words, I'm just trying to describe to you what looks like the normal curve. Okay, so assuming that z is normally distributed with a mean of 0 and a standard deviation of 1, find the probability that z is between 1 and 2. Now, let's just check. P is between 1 and 2. 1 and 2. They're both positive. So in other words, we now want to find out what's the probability that we are here in this region. There. Okay? We want to find out what's the probability of being in that region. Now, what we have to do in this case is we have to take both separately. And I want you to think about this. If I was to get the area of the curve all the way behind 2, and then get the area of the curve all the way behind 1, and subtract what is behind 1 from what's behind 2, wouldn't that give me the shaded region? I'll say that again. Let's work out, first of all, this is z-score of 2, z-score of 1. Let's work out what the area is, all of this area here, to the left of 2. The tables will give me that, no problem. Then let's work out what's to the left of 1. The tables will give me that, no problem. But I don't want that. I want what is between those two. So therefore, we're going to work out the probability of z being less than 2 and take away from that the probability of z being less than 1. See? Okay, so that's what we're going to do here. So we go to the tables. What's the probability of z being less than 2? Well, the probability of z being less than 2 is 0.9772. That comes directly from the tables. What's the probability of z less than 1? Well, go to 1, and that's 0.8413. And when you take those away from each other, 0.9772 minus 0.8413, we end up with 0.1359. 0.1359. That's it. So the probability of being between those two values is 0.1359, or, as we said already, 13.59%. But I think I prefer to use decimals when you're dealing with probability and not percentages, unless you're specifically asked. Okay, let's do another one. The probability that z is between minus 1.4 and minus 1.145. Now again, let's see where these are. First of all, 0 is the mean. Minus 1.4 is about here. Yeah? And minus 1.145 is about here. So in other words, there's a tiny, we're just looking for these two. In between these two, that's it. So this is minus 1.4 and this is minus 1.45. Now, they're negatives. So what do? Use symmetry. Use symmetry. We can't use negative z-scores, so let's bring these symmetrically to the other side. And let's use 1.45, which would be here somewhere. Yeah, 1.45, that's too far over. Let's go past the halfway mark. Let's just take that off there. So 1.45. So 1.45 is about here. Okay, and then the next one is here. So there's plus 1.45 and there's 1.4. So instead of trying to get the area between the two negatives, which we can't do, switch it around by symmetry. Now, if we get the area between these two, it's exactly the same. It'll give it the same percentage. So we are not going to use these. Nope, we're not going to use any of them. We're going to switch over. We're going to go using symmetry to the other side and do it this way. So now, what's the probability that z is less than 1.45? That's everything to the left of 1.45. Then I want to take away from that the probability that z is less than 1.4. So you go to your tables, 1.45, and 1.45 is 0.9265. And the probability of z being less than 1.4 is 0.9192. So 0.9265 minus 0.9192 comes out as 0.0073, better known as 0.73%. So it's a tiny, tiny slither of percentage of the whole thing, only 0.73%. Okay, again, I'm going to leave you that one there, do yourself, and I'm going to ask you to engage now with page 100 and page 101 and have a look at the following questions and make sure you can understand how to do your probabilities of z-scores before we move on to actually finding the z-score itself. So you can pause this now, work on those questions and come back when you've done the questions. Okay, so just to stick with the normal distribution table, already we know that a normal distribution table is a table that is given to us, or a graph that's given to us when data is randomly and normally allowed to be gathered. Okay, so it's distributed normally. Since all normally distributed sets of data are measured in different units, so for example, IQ is measured in IQ units, mass is measured in kilograms, height is measured in centimeters or inches or feet, whatever it is, they're all different. So what do we do? How do we get feet? How do we get centimeters? How do we get IQ units? How do we get kilograms? How do we turn them into z-scores so that we can use the table? And the answer is by using a formula. It's called the z-score formula, and it is in your tables. Okay, the z-score formula is the following. Now, what does all this mean? The z-score of a certain piece of data. So there is your statistic. Okay, so that's the statistic I am testing. The statistic minus the mean over the standard deviation. Now, you'll be delighted to know these are all going to be given to you. So the statistic will be the person's height. Okay, the mean will be the central value of a group of people's height, and the standard deviation will be something that's given to you that has been already calculated with this body of people. The symbols, this symbol here is called mu. Yeah, so it's P N U, mu. All right, and then this one here, as I told you already, is sigma. Okay, so just remember that mu. So PMU, that's mu and that's sigma. But the formula is extremely important. So if we give you any statistic that is not a z-score, you have to turn it into a z-score by taking the statistic, removing the mean, and dividing that difference then by the standard deviation, that body of data. And that'll all be given to you. So it's quite a straightforward thing to do in terms of the calculation. So X is the variable under test, or the statistic, as I said already. Mu is the mean, and sigma is the standard deviation. So here's an example. The mean total score, the mean total score, what's that? That's mu, okay, is 137, okay, with a standard deviation, sigma, of 10. If you go to a match, what is the probability that there will be 150 or more points scored by the two teams? Now, that 150, that is the statistic under test. So what do I want to do? What's the probability that there will be 150 or more points scored? So the probability that the points scored is greater than or equal to 150. So that's what we're writing down in English. What is the probability that the points scored will be greater than or equal to 150? Notice it's not a z-score yet. So I have to turn this 150 into a z-score. Let's do that. What are we told? Z is the statistic under test minus the average divided by the standard deviation, which will be the statistic under test is 150 minus the average, mu, 137, over the standard deviation of 10. So what does that give me? Turn on your calculator. So you've got 150 minus 137. Just do the whole thing together over 10. Calculator has a fraction function, which is very handy, and that comes out as 1.3. So now we want to rewrite this as, what is the probability that the z-score is greater than or equal to 1.3? So we can't use the point scored because that's a normal distribution, it's a random distribution, but we do turn the point scored into a z-score. And now let's have a look. The first thing I would always suggest you do is take a sketch of where this thing actually is. Okay, where's 1.3? 1.3 is about there. Okay, what do I want? I want the probability of z being greater than or equal to. Now immediately we've got a problem. And the problem is that tables don't give me the area to the right. Tables only give me the area to the left. So therefore, what I can do in this situation here is I could work out what area is to the left of 1.3 and take it away from 1. So in other words, this will be 1 minus the probability of z being less than 1.3. It's a bit like those questions in probability at least one go or at least 2 tries, yeah? So you're just doing the opposite. You can't get area to the right, you can only get area to the left, so we rewrite it as this, which is going to be 1 minus. So what do? You go to your tables. What's 1.3? 1.3 is 0.9032. And what's that going to give me? Well, 1 minus 0.9032 comes out as 0.0968, which means there's a 9.68% chance that 150 or more points will be scored by the two teams. So make sure you practice the previous part. Be very comfortable with turning numbers into z-scores. Be very, very comfortable with finding the probability associated with giving z-scores, whether it be to the left or to the right, and negative z-scores as well, before you attempt these questions. Be very comfortable. Only when you're comfortable, move on. Okay, so I have the question up there for you. Change 150 to a z value, which is 1.3. Notice That 1.3 using the normal curve in the tables, as I told you already, will give you the area that is to the right, but tables don't do that. So it's 1 minus the area to the left. Okay, so what is P of Z 1.3? Now we've done this already, so we'll just do it again quickly. P of Z greater than 1.3 is the same as 1 minus the probability of Z being less than 1.3, because we can't go above, we can't get above 1.3. So instead of getting above 1.3, which is this thing here, we take the whole lot and we take away what's below. All right, and I did that already. 1 minus, as I told you, what did I say 1.3 was? 0.9032, 0.9032. So that gives me 0.0968, which is 9.68% chance. Okay, so let's have a couple of examples. Another 5 minutes and we'll be done, and then we'll let you off with some examples yourselves. The heights of women in Ireland are normally distributed with a mean of 163 and a standard deviation of 5. Now, when you're reading, highlight and start to write down. A mean, first of all, they are normally distributed. That means that the normal curve can be used. If it's not normally distributed, if it's skewed, forget it, can't calculate. Okay, normally distributed with a mean of 163, standard deviation of 5. A film producer is seeking an Irish actress whose height is between 170 and 175. The director says to the producer, "You are being too fussy. The chance of finding an actress with the right height is less than 5%. Is this statement correct?" Now look at what I've circled. Normally distributed, it's a natural distribution. You can use the normal curve and the probabilities associated with them. Okay, a mean. So mu is 163. Standard deviation of 5. Now here's what we want. We want the probability that the height of the ladies is between 170 and 175. But height is not a Z-score. So the very first thing I've got to do is turn both of these into Z-scores. And then I'll come back when I have them in Z-scores and try and work them out. So let's take 170. What's the formula? The Z-score is the statistic under test minus the mean divided by the standard deviation. So that becomes 170 minus the mean, we said it was 163, all over 5. So 170, that's 7 over 5, and 7 divided by 5 is 1.4. Okay, so that's the first Z-score. Now, I want to turn, what's the other height we have? 175. So the Z-score for 175 is 175 minus 163 all over 5. So that's going to give me 12 over 5, which comes out as 2.4. Okay, so that goes over here. Now, let's take a look and see where these are. So you've got your Z-scores. Next thing we do is look and see if we can find them on the normal curve. Where would they be? Well, 1.4 would be here. There's 1.4. 2.4 would be somewhere here. And what I want to do is find out what percentage is between these. Okay, that's what they're asking me to do. Now this is okay, and it's fairly straightforward, because if I want to get this area between two lines, between two Z values, I first of all work out what is the total area to the left of 2.4, and that's easy because the tables will give you that. Then I'm going to find out what's the area to the left of 1.4, but I'm going to take it away from what I got for 2.4. So in other words, the probability of Z being less than 2.4 minus the probability of Z being less than 1.4. That's exactly what we want to do. So let's take a look at our tables. 2.4 gives me an answer of 0.9918. The Z-score for 1.4 is 0.9192. So 99.9918 minus 0.9192 comes out as 0.0726, which is 7.26%. So in other words, there's a 7.26% chance of finding a woman between these two heights. What did the director say? You're too fussy. The chance of finding an actress with the right height is less than 5%. Rubbish. The chance of finding a woman between those two heights is 7.26%. So his statement is not correct, and I have justified my answer through mathematics. Page 102, question 3. The heights of men in Ireland are normally distributed with a mean of 168. So again, I'm going to start writing. They're normally distributed, so I can use the normal curve, with a mean, mu, of 168 and a standard deviation of 6 centimetres. Find the probability that an Irishman selected at random will be greater than 180 centimetres in height. So I want the probability that the height will be greater than 180 centimetres. Let's just put in the wrong symbol there. Should be greater than. So just be careful when you write them out, you put in the right thing. So height is greater than 180. Okay? But height is not a z-score. So the very first thing I've got to do here is turn height into a z-score. So z is equal to the statistic under test minus the average divided by the standard deviation. So in this case, 180 is what we're testing, minus 168, which is the average given at the top, divided by 6. So throw it all into your calculator. 180 minus 168 divided by 6, and that comes out as 2. Okay, so now I want the probability that z is greater than 2. Okay, let's see where that is on the normal curve. And I would advise you draw one always. 2 is roughly here. Okay, so there's 2. Now, I want the probability that we are above 2. So I want that area. But tables don't give me the area to the right. Tables only give me the area to the left. So instead, what I'm going to do is I'm going to count that as 1. And I'm going to remove the probability that z is less than or equal to 2. So in other words, I'm going to take all that as 1, and I'm going to remove this here. Because in the tables, when I look up 2, the tables will give me the area to the left of 2. And 2 is 0.9772. So it's 1 minus 0.9772, which is equal to 0.0228. So 0.0228, which is what? 2.28%. So find the probability that an Irishman selected at random will be greater than that. There's a 2.28% chance that the Irishman will be greater than 180 centimetres. Okay, the annual number of hours of sunshine in Ireland is normally distributed with a mean of 1,150 hours. So here we go, 1550, and a standard deviation of 150. Okay, what is the probability that next year there will be less than 1,300 hours of sunshine in Ireland? So what's the probability that the sunshine hours will be less than 1,300? Guess what? Sunshine hours are not a z-score. Change it. Z equals x minus mu over theta. Fill them in. 1,300 is what I want to change. Minus mu 1,550 all over sigma 150. Okay. Now, in this case, 1,300 1300 minus 1,550 all over 150 works out a z-score of minus 1.67. So that's minus 1.67. So now I have to rewrite this probability. And I'm going to rewrite this probability that the probability of z is greater than minus 1.67. See? So now, where's that on my normal curve? Well, on my normal curve like this, what have we got? Normal curve, like that. Where is minus 1.67? It's down here somewhere. Minus 1.67. What do I want? I want the area that is less than that. So I want this area here. Now, yes, it's the area to the left, but there's no negative z-scores in your tables. So instead, what I'm going to do is I'm going to take the same value, but this time I'm going to use 1.67 with the area in front, which, with the previous question, you take the whole thing as 1, and it's going to become 1 minus the probability that z is less than 1.67. See that? So that's where you're using your symmetry. So even though I can get the area to the left of this here, the tables don't give me negative z-scores. So switch it around, make it positive 167 with the area to the front, but the tables don't give me the area to the front. But that's easier to solve, because the area in the front is the same as 1 minus the area in the back. And that's going to give me 1 minus 0.167 from your tables, 0.167, and that comes out as 0.9525. So 0.9525, and 1 minus 0.9525 is equal to 0.0475, which is 4.75%. Now I'm going to leave the rest of these for you to do. These are very, very straightforward. Okay, I've spoken long enough. You can do part 2 and part 3 yourself. You can then take a look at the next example, which is question 12. And I want you then to work on the questions on page 102 and 103. And again, if you have any difficulties, shout. If not, we'll have our live class on Thursday. You can bring your difficulties if there is any there, or if there's any points you need for further clarification. We will take a look at those in the live class on Thursday.